Okay, so just wanted to talk a little bit about our lab. In particular, I wanted to talk about table 2. Where did it go? Okay, so because sometimes when you read a research paper, they'll have all these tables published or printed, and sometimes the way they're presented is not 100% intuitive, okay? And so what we're looking at here is, we're measuring these ADHD, rating scale 4 or RS4 scales, okay? So this basically just gives someone an ADHD rating, okay, from like, I guess 0 to whatever, okay? You get points, and if you're exhibiting traits of ADHD, you get these numbers here. Okay, so they have hyperactivity and inattentiveness, and apparently you can just add those two together. All right, and so at baseline, they measured, they randomly assigned 27 people to placebo, and those 27 people had a baseline hyperactivity measure of 10.3 and a baseline inattentive measure of 15.6, okay, which gives them a total baseline of 25.9. The people that were randomly assigned to the treatment, their total baseline was 27.6, okay? And so, we have these p-values along this edge, and then there also gives a confidence interval, all right? So, what does all of this mean? So basically, at baseline, meaning when they first started, the placebo, what we're saying is, we're like 95% confident that the baseline measure for the placebo group is anywhere from 22.9 to 28.8, okay? And that the baseline measure for the treatment group is anywhere from 24.6 to 30.7, okay? That's what these confidence intervals mean. This p-value of 0.32 represents, is there a significant difference between 25.9 and 27.6, okay? So the difference between 25.9 and 27.6 is like 1.7 points. Is that significantly different from 0? And the answer is no, okay? Our p-value says this, you would get such a difference with probability 0.32, okay? And then when we look at difference baseline to week 8, we're looking at how 25.9 reduced to 20.7, and 27.6 got reduced to 23.22, or I think just 23.2. I think this is a typo here, all right? And so the change from here to here is a reduction of 5.2 points. And the change from here to here is a reduction of 4.4 points, okay? And so if we create the confidence interval, we go from negative 9.4 to negative 1.1 here, okay? That would mean, is this negative 5.2 significantly different from 0, or is there a significant difference from 25.9 to 20.7? And the answer is yes, okay? Because 0 is not in our interval, so we have evidence that that placebo made a difference between baseline and week 8, okay? A non-zero difference between baseline and week 8, and that's what we have here. Over here with the treatment, our confidence interval goes from negative 7.9 to negative 0.9, okay? So here we would say we have evidence that the treatment made a difference that wasn't 0, a non-zero difference, right? Okay, because our confidence interval does not contain 0. So far, so good? Okay, but we look at this p-value, and then we get this thing of 0.76, right? And so what this is saying, let's think about what our null and alternative hypothesis would be. Yeah, so the null hypothesis would be that placebo and St. John's wort, or H. perforatum, okay, whatever that is, the placebo and treatment are have the same effect. Okay, same effect between baseline to week 8. We're saying that the two groups have the same mean effect. And then the alternative, we would expect the treatment to be more effective than placebo, right? Okay, so our alternative, so if I were to write these, over here, my null hypothesis would be something like the mean of the, this is going to be, I'm going to just write baseline, okay, so mean for placebo is equal to mean for treatment. And the mean placebo is basically the mean difference baseline of week 8, right? And then the alternative, because we're expecting treatment to be more effective, we would expect mean placebo to be less than mean treatment. Okay? What do we notice? We see, when we look at our data, our y bar 1 is negative 5.2. Or, I'm sorry. Okay, I'm just going to turn it into 5.2 just because. And our y bar 2 is 4.4. Okay, and so what we're seeing is that the placebo actually has a larger effect than the treatment group. Okay, so this does not line up with our directionality, right? So our data does not support the directionality. All right, and so what we're seeing is that if anything, the results of the experiment seem to indicate that placebo is more effective than the treatment. Okay, but when we compare, is there a difference between placebo and treatment, or do we have evidence that the treatment is more effective than placebo? The answer is no. We would get, how different is 4.4 from 5.2? Okay, that's a difference of 0.8. Is 0.8 different from 0? And the answer is no. The p-value is ending up very large. Okay, does this make sense? So, yeah.
I have a question. Why is the p-value so large? Don't they usually give you? Oh wait, I'm sorry. Never mind. I answered my question.
Oh, okay. So, well, part of the reason why the placebo is so large is because our data doesn't even support the directionality. In fact, it goes the other way. Okay, and so if we were to kind of take our shading, we're expecting this value to be less than the other value, but it ends up being larger. So we end up going on this side, having a 5.2 minus 4.4 is positive 0.8. We're expecting a different, under the null hypothesis, we're expecting a difference of 0. And so because we're looking at the area to the left, we're getting shaded area greater than 0.5. Yes?
Are you also accepting other questions related to this?
Sure. I will. I wanted to bring up this one because I think this is the I don't know, the most not important part of the lab, but just I think sometimes making sense of the results tables is can be tricky. Okay. And this is just one research article. If you were to read another research article, the results tables might look totally different, and you might have trouble making sense of it. So you kind of have to, when you see a p-value printed somewhere, you should be asking, what were the null and alternative hypotheses associated with that p-value? Okay, and once you can, if you ask yourself that question, based on the context of the problem and the data, you might be able to figure that out, okay? And once you figured out what your null and alternative hypotheses mean or are, then the p-value will make a lot more sense, okay? Rather, I think sometimes, well, you know, I don't know about you guys. I don't know how many research articles you have to read, but you know, if you go through like medical research articles, sometimes you just, and I think this is, recently p-values have come under a lot of attack because we've kind of removed the critical thinking out of research and just said, oh, did you get a number smaller than 0.05? Great, and that's not how research really should be done, okay? So, but anyway, yeah, so go ahead, another question.
I just had a question about like directionality.
Uh-huh.
Wilcox-Whitney tests.
Okay.
Just like the first problem on the homework.
I'm not going to save this slide, just FYI. Okay.
B was like it was directional, and it was that like toluene increases dopamine concentration.
This is for Wilcox-Whitney?
Yeah.
Okay.
And I was just wondering like what the other, like how you would even calculate like the opposite directionality. Like just like how would those statistics make sense? Do you know what I mean? I was just having a hard time conceptualizing like.
Okay, let me let me see if I can pull up this question here. This one right here?
Yeah, just like what if the null hypothesis had been or if the null hypothesis had been toluene has no effect, and then
if it asked for a directional alternative?
Yeah, but it said like the control increased. I just like.
Okay, so okay, if I'm understanding the question correctly, you're asking what would our hypotheses be if they were non-directional, what would our hypotheses be if they asked for a directional test?
No, I understand that.
Okay.
I think I answered my own question. Like if it were going the other direction, if it were like toluene
decreases.
Okay.
Dopamine concentration.
Yeah, just like, and you get the same p-value.
Well, okay, you would not. You would actually. So, you would get the complement to the p-value here. Okay. So basically, you have your data, and then you get your U statistic over here, and then you get your U statistic over here, right? And this is toluene, and this is what was the other one? Control. Okay. So I don't know what these numbers came out to be. All right, but basically, if our the null hypothesis is basically same distribution. And if we had a directional alternative, we have two choices, all right? So directional alternative is basically toluene is larger than control, all right? I'm going to just write toluene population. This is very sloppy, okay? So it's not that toluene population is greater than control. It's just the distribution associated with toluene population generally, right? Okay, and then the other one would be the directional alternative would be that toluene population would be smaller than control, right? Okay, so let's say your U statistic over here ends up, I don't know, let's say 50 and 6 or something like this. I'm making these up. Okay, so what we have at this point is that if we had a directional alternative, our data, the number associated with toluene is indeed greater than the number associated with the control, okay? So our data supports the directionality of the alternative that has toluene greater than control. Okay? And so here you would continue the test. Dot, 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 and then maybe you get your p-value is between, I don't know, 5% and 1%. Okay, I'm making these numbers up. Okay? On the other hand, let's say your directionality was this. Your alternative was stated this way. Okay? So if we used this alternative, that toluene is greater than, oh, wait, no, the other one, toluene is less than control, okay, our data does not support that. Okay, and so at this point we could just stop and say we will have no evidence to support the alternative. That's one way to go. Okay, if you insisted on continuing the test to get a p-value, okay, you still have the same exact thing, except now because you know your data goes in the opposite direction of the alternative, then your p-value will be basically 1 minus these values. Okay, so probably suggestion will be, just stop the test and say we do not have evidence to support the alternative.
Okay. Yeah.
But if you put it into a computer, the computer is going to give you a p-value. And then so if you insisted and you continued the test, then what you're going to get is you're going to get your tail area is less between 0.05 and 0.01, okay? But to go from your tail area to your p-value, you would subtract your tail from 1, and you would get 0.99. Your p-value would be between 0.99 and 0.95, and so this is what you would end up having, okay? And that's fine, okay? And if you punch it into a computer, you would get something like that. So sometimes if you specify a directional alternative, you could very well get p-values of 98% and things like that. And that basically means your data does not support the alternative. If anything, your data kind of supports the opposite of what your alternative is saying. Yeah.
Right, and if it weren't as obvious that there was a difference, then you wouldn't be rejecting your null hypothesis in the first place.
Over here, like if your p-value.
Yeah, if like the values were closer together.
Okay, well, even then, one of them will probably be larger than the other. I mean, they could be equal, and then you would have no evidence to support the alternative. But maybe you get u is equal to I don't know, 39, and u over here is like, what would that be? I don't know, 27 or something like that. Okay. Even still, this still supports this notion that the toluene is greater than the control, rather than toluene is less than control. Okay. Okay. And again, this is just one example of a non-parametric test. And the key behind non-parametric tests is that we're not using symbols like mu. We're not putting any kind of assumptions on the distribution. We're not using the central limit theorem to say this is why. Here's the mathematical theory that backs this up. We're just saying numbers are numbers. Let's see what's bigger. Which depending on what field of research you go into, there may or may not be an importance placed on non-parametric statistics. Okay, so a lot of times when you have things that behave, quote, nicely, like normal-ish distributions, non-parametric statistics will almost never be used, just because things behave nicely. But then in other situations, you have extreme outliers that can't be coerced into nicely looking things, and so nonparametric statistics play a bigger part. A lot of times when there are outliers, people will do a log transform. They just take the logarithm of all the data, and then a lot of times that turns things into normal distributions. So like income is extremely skewed, but if you apply a log to it, it becomes more normal-ish. Not completely, and you get these exponential things in any situation where there's kind of a positive feedback. So like with income and wealth, there's this notion of the rich getting richer, and it definitely, like when you have a lot of money, you have the means to make even more money faster, and so so you get people over here taking off even at greater speeds. But it's just a phenomenon that exists. So okay. All right. Shall we? We'll move on then. And I forgot my textbook. Oh well. I've got this version here. Okay, so we'll today we're entering chapter 11, which is all about ANOVA. Okay, and so let me just pull up my data table that I want to use. Okay. Okay, so today, chapter 11. We are covering ANOVA. Okay. And specifically in this class, we're only going to cover one-way ANOVA. But I will mention some of the other forms of ANOVA that exist. ANOVA stands for Analysis of Variance, okay? And that is a good summary of what it is, okay? So if we think about, what is variance? Is anyone willing to offer, a definition of what variance is? Yeah.
How far away the values fall from the mean?
Yeah.
Average?
Yeah. So it's the variance can be thought of as the quote average squared distance from the mean. Is there a question there?
No.
Okay.
I thought that was the definition for standard deviation.
Yes. The standard deviation is the square root of the variance. Okay. So so the standard deviation is equal to the square root of the variance. So if it sounds familiar, it's probably because it is. Okay. So the variance can be thought of as the quote unquote average square distance from the mean. And then if we take the square root of that, we end up with the standard deviation. So it's this measure of spread, okay? And just conceptually, we can just think of it as, a numeric summary that tells us the values in our data are different from each other. Okay? And so when we're talking about the analysis of variance, we're going to take kind of this total amount of variance, and we're going to try to break it out into different components. Okay? And we're going to try to say, you know what? If we looked at people's heights, everyone has a different height. Okay? Some people are tall, some people are short. Okay? What we're going to try to do is, rather than just have this general statement that says everyone has different heights, we want to kind of assign some amount of that total variance that exists and say part of the reason why people are different heights is because some people are men and some people are women. And in general, men are taller than women. Okay? So let me just kind of write this down. So ANOVA, this analysis of variance, with ANOVA we will try to, quote, break apart the variance into, you know, different sources. Okay. And so, you know, if we think about people, well, you know, people and their heights, people's heights, okay, we can just say, you know, everyone, you know, people have different heights, right? You know, there is variation in heights. Okay? And maybe we can assign some value to this variation, okay? And what we're going to do is we're going to try to break apart the variation into to two parts, okay? So prior to breaking it up, if somebody says, you know, if a child asks you, why are people different heights? You can say, people are different heights because people are different heights, and everybody's different, right? So, I know this is very silly, but, you know, why are people different heights? Okay, so, and the answer, before ANOVA, your answer is, before ANOVA will just be, everyone is different. That is why they are different heights. Everyone is different. People have different heights, okay? You know, why do people have different heights? Because everyone's different. You know, I mean, that's a silly answer, okay? So with ANOVA, what we're going to do is we're going to take this total variation, and we're going to say part of the reason why people are different heights. So one source of variation will be the sex of an individual. Okay? And then the other source, so this is what one way ANOVA does, okay? We just come up with one source, and then the other source will be everyone is different. Okay? So if the child, after ANOVA, your answer to why are people different heights, your answer will be everyone is different. This is always part of the answer. Everyone is different. Okay. Also, there are men and women, or boys and girls. This sounds more ridiculous when I say it out loud. Okay. Also, there are men and women, and in general, men are taller than women. Okay. Okay, and so with ANOVA, we will be breaking apart the variation into different sources. One of the sources will always be individual differences. Okay, so even though in general men are taller than women, you can have tall women, you can have short men. Okay, so there's always going to be individual differences. That's always going to be a source of variation. Okay. But we can, rather than just saying there's this much variation between everybody, we can say part of the variation is because there are two distinct groups in the population, men and women. Okay? Does that make sense? And that's what we're doing with ANOVA. We're just breaking apart that variation into, trying to break it apart into different sources. One being group differences, and the other being individual differences. Okay, and so with one-way ANOVA, we're just picking one other source other than individual variation. Okay, and so we'll have different groups for that one other source of variation. Okay, with the other forms of ANOVA, you can have, you know, maybe you'd say, oh, people have different heights because of their sex and because of their ethnicity or something like that, or you know, race or whatever, you know. So you'd have different kind of grouping things, and you can have more than one. So with one-way ANOVA, we have one other source of variation other than individual differences. So everyone is different. This is called our, you know, just individual differences. Okay, individual differences. This can be thought of as within group variation, also called residual variation. Okay, and then over here, we will have this will just be known as our between group variation. So the total variation can be separated into two parts. Part of the variation is because the groups are different from each other, and part of the variation is just the individual variation or individual differences that we'll never get rid of as long as variation exists in some form. Okay, so this is kind of the big picture concept of ANOVA. Right? We have kind of already done something similar to this when we're talking about t-tests, right? So when we do t-tests, we're not breaking apart the variation, but we come to the conclusion that group 1 has a different mean than group 2. Okay? So, but one thing that ANOVA allows us to do is it allows us to handle more than two groups at a time. Okay? So with ANOVA, we are essentially going to compare group means. Okay? We have already learned how to do this with t-tests. Compare two group means with, well, really, t-tests and confidence intervals. Okay. A key difference is that ANOVA will allow us to compare more than two group means at once. Okay, so if you have 3 groups or 10 groups, you can use ANOVA to compare the means between all 3 or 10 groups. There is a downside, though, and it's that the alternative hypothesis for ANOVA will always be non-directional. Oh dear, what just happened? Okay, so with ANOVA, for ANOVA, or I'll say for one-way ANOVA, your null hypothesis, let's say you have one-way ANOVA and you have 4 groups. Okay? Your null hypothesis is all 4 groups have the same mean. Okay, or symbolically, we would write mu1 is equal to mu2 equal to mu3 equal to mu4. Okay, which is equal to mu all by itself. This is called our quote grand mean. This is the mean of everyone. Okay, so we're basically saying all of the group means are equal and they're all equal to the mean, grand mean for everyone. Okay. There's an alternate formulation for one-way ANOVA. Okay, so the alternate formulation is to say mu sub I is equal to the grand mean plus some group effect tau sub I. So this is saying, you know, a group mean, group I's mean is equal to the grand mean plus the group I effect. Okay, so if the grand mean, if the average height of all people combined is like 5'8" or something like that, all right, or maybe 5'7", maybe the group effect of being male is plus 3 inches. Okay, so that your group mean is not 5'7", but 5'10". The male's average is 5'10". And then maybe the group effect for females would be like minus 2 inches or something like that. So that the group average would be 5'5" or something like that. Okay, so this is an alternate formulation. So in this alternate formulation, the null hypothesis would be that tau sub 1 is equal, all of the group effects are equal, and they're all equal to 0. Okay, so it's just different notation. And you know, if you ever take stats in the future, you might encounter either notation. And I'd say this is probably easier to understand, but this is probably more common in the literature, to have group effects. Okay, but can we see how these two are essentially saying the same thing? Okay, so all we're saying is that you know, mu sub 1 would be the grand mean plus some group effect of tau sub I. Okay, the alternative hypothesis will be at least one group mean or group effect, however you have it written, at least one of the group effect or one group mean is different from the others. Okay, or at least one group effect is not 0. And so, our alternative hypotheses are will always be non-directional if there's more than 2 groups. Okay. I'll say three or more groups. So if you have 3 or more groups, you're always going to have a non-directional alternative. So you might reject the null hypothesis, but it will not tell you which group was the different one. It's just going to say, well, at least one group was different. The end. And it won't say the group that was different was this one. Okay, so that's one of the weaknesses of ANOVA. And this gets back to this, there's kind of this problem, unavoidable problem in statistics called the problem of multiple comparisons. So if you have multiple groups, it's hard to pick out which group is truly different from the other groups. Okay, so problem of multiple comparisons. Okay, so with many groups, it becomes difficult to distinguish one group from another, or I'll say, one group mean from another group mean. Okay, so we might be able to, maybe we have 10 different groups, right? And we can line up our group averages from least to greatest. Okay, so maybe we can arrange them, and so we get y bar 1 is less than y bar 2 is less than y bar 3, so on and so forth, y bar 4, etc., 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 up to y bar 10. Okay, and perhaps, and we haven't gotten there yet, but maybe our results tell us, our results from ANOVA, I should say, tell us that there is evidence that not all group means are equal. Okay, so maybe we can reject the null hypothesis that all the group means are equal. But is it, even if we've lined them up from least to greatest, where does the difference happen? Is it that group 1 is much smaller than everybody else, or is it that group 1 and 2 are indistinguishable from each other, but they're different from groups 3 and 4 or something? It becomes difficult, right? Like, you can imagine, this is not a great analogy, but you can imagine going to the hardware store, right? And then, they got all those paints, right? They've got like that swatch of paints, the thing, and you can get like shade of brown, slightly darker brown, ever so slightly darker brown. And then you say, okay, these colors are different. But then someone says, okay, well, at what point do you say the this brown is too dark and this brown is too not dark enough, or whatever? It gets a little bit tricky. Okay, and we could say like, well, why not just do a bunch of t-tests, right? Why not just compare y bar 1 versus y bar 2 to see if mu1 is different from mu2, right? So, you know, like one solution is just to do multiple t-tests. Okay, so we could say, you know, the null hypothesis could be mu1, is that equal to mu2, right? And then, you know, your data uses y bar 1 versus y bar 2, okay? And then you can have another, you know, this is test 1, and then test 2 will be mu1, is that equal to mu3, you know, and then so on and so forth. Mu1, is that equal to mu4? And then you'd have okay, how many tests would I have to do? 16. Let me see. So if I've got 10 groups and I'm doing pairwise comparisons, right? So this would actually be 10 choose 2. This is how we would get this. There would be 45 comparisons to make. Okay? So we would have a total of 45 tests to perform. Okay, so test 45 would be mu9 versus mu10. Okay? And you know, this is a lot of work, but you know, with the help of a computer doing 45 tests, it's not too hard, okay? But there's a problem with trying to do 45 tests. Okay? And what is the problem with just doing 45 tests?
Not comparing all of them to each other.
Well, we're doing every pairwise comparison, right? So we've got 10 different groups, and we're going to do like 1 versus 2, 1 versus 3, 1 versus... We're going to do all 45 possible, I guess, handshakes, right? Between the groups. So we have a total of 45 tests to perform. The problem is, okay, so think about every time we do a test, let's say we used alpha equal to 5%, okay? What is alpha equal to? Alpha is the probability of what kind of error? Type 1 error. Thank you. Yes, so alpha is the probability of type 1 error. And what is type 1 error? Mistakenly rejecting the null hypothesis, right? So the null hypothesis is true, but we incorrectly reject it, okay? So every time we do a test, we have a 5% chance of making a mistake, right? So there's a 5% probability of a type 1 error. If I do 45 tests, do you think I can get through all 45 tests without making a single type 1 error? Probably not, right? So it's like shooting, even if you were the best free throw shooter in the world, okay, well maybe not best, but if you have a 95% free throw shooting average, okay, you'd make a lot of free throws. But if you had to take 45 of them, you're probably going to miss one of those, right? Or a few of those, okay? And so when you perform a whole bunch of tests, and it's not quite fair to say treat it as independent, because they're not independent, they all use this, they share some common data. But the idea of trying to perform a whole bunch of tests and expecting not to make a type 1 error after 45 tests, that would be a bad assumption to make. And so probably somewhere along the way you're going to make a type 1 error, and so you can't tell, and you don't know if you've made a type 1 error or not. And so you might say mu4 is different from mu5 when in reality they're not, okay? Because that would be a type 1 error when you've come to the conclusion that they're different when in reality they're not. Okay, so total of 45 tests to perform. So if alpha is equal to 0.05, we will almost certainly make a type 1 error somewhere along the way after performing t-tests. Okay, and so this problem of multiple comparisons, there's no simple strategy to solve this. Okay, it just exists. We can't avoid it. And so, you know, research has been done. There's a good amount of literature on possible solutions and possible ways to deal with it, but I think it's just something that's inherent to this process of trying to make conclusions from limited data. Okay, so let's get into the kind of the nitty-gritty of performing one-way ANOVA. And so for our example, I'm going to use this data. Which has been nicely summarized for us. Okay, so here I've got this table exists in your text, and you can copy it down. Oh, maybe I need to make that larger. Okay, so what we have is we're looking at this is artificial made-up data, but they have some nice properties. We're looking at the weights of lambs, and apparently we have 3 different diets that we can give them, and we just said how much weight did these lambs gain after, I don't know, a few weeks on these diets. Okay, so you know, so this lamb on diet 1 gained 16 pounds, where the other 2 only gained 8 or 9. Okay, and on diet 2, all of these lambs gained, you know, a bunch. This one gained 21 pounds, but this one only gained 9, and so on and so forth. Okay, so you know, a bunch of lambs, a bunch of different weight gain values. All right, so our null hypothesis is going to be that the weight gains for the population of the lambs who might take diet 1, diet 2, and diet 3 are all the same. Okay, so this basically says the amount of weight gained is the same for all 3 diet groups. Okay, and then our alternative hypothesis will be at least one of these diets produce a different amount of weight gain. Okay. You don't have to write all of these summary statistics. They're there, but you don't have to write them. Okay. I'm gonna flip to the next slide. All right, and I'll put this table. It's just gonna be a little bit smaller here. Okay. Okay, so to kind of illustrate this, I'm going to draw some dot plots here, okay? So this will be, I'm going to get a dot plot for diet 1, diet 2, and diet 3. All right, and I'm going to go, this will be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20. Okay, and then let me just kind of make some make a grid here. All right, so all I'm going to do is I'm just going to graph these data points. So on diet 1, we have a lamb that gained 8 pounds. We have a lamb that gained 16 pounds, and a lamb that gained 9 pounds. Okay? On diet 2, we have a lamb that gained 9 pounds, a lamb that gained 16. This one gained 21. This one gained 11. And this one gained 18. And then on diet 3, we have 15, 10, 17, and 6. Okay? And so if I put all of them together, this is what I would have here. Okay? So all the data points together would look something like that. Okay? And so here we would have, the concept here is, this is the total amount of variation. Okay? And we're going to basically take these data points and we're going to like spread them out and say, oh, okay, some of these data points belong to diet 3, some belong to diet 2, and some belong to diet 1. Okay? And then the question is, are the mean weight gains for diet 1, 2, and 3, are they all the same, or is at least one of these significantly different from the others? That's our question, okay? So looking at it, does it seem like there's a significant difference in the average weight gains between diets 1, 2, and 3? Maybe, maybe not. Okay, so what I'm going to do is I'm going to graph the group mean for each of these things. Okay, so if I did 8 plus 9 plus 16, 8 plus 9 plus 16, if I add those up, I would get 33, and 33 over 3 data points gives me a y bar of 11. Okay, and so our table summarizes these nicely, and so effectively I would get a group mean right there of 11. Okay, if I did this for diet 2, its group mean is 15, and for diet 3, its group mean is 12. Okay, so I have these 3 different group means. Okay. And the grand mean, okay, we have this concept of the grand mean, which will we indicate with y double bar. Okay, the grand mean would be if I took all of these, how many points do I have? 12 data points, added them up, and divided by 12. Okay, so this would be, all 12 points together divided by 12. Okay, so I would have to add all of these up, and if I did that, it's created these sums for me. I would get 33 plus 75 plus 48 divided by 12. I would get an average of 13. Okay. Now, it's important to keep in mind that the grand mean is not the average of the three mean values. Okay, so if I did 11 plus 15 plus 12 and then divided by 3, I would get something else. I would get 12.67. Okay, so the grand mean is not the average of the three group means. To get the grand mean, what we have to do, okay, we either have to add up all of the data points that we have, okay, and sometimes this is not available to us. So if we only have, you might only have the summary table, okay, and so what you have to do is you kind of have to recreate the sum by doing n times a group mean, y bar, right? So if I did 3 times 11, right, the average of these three numbers is 11, and if I did 3 times 11, I would get back the total of these three numbers. And if I did 5 times 15, I would get back the total of these 5 numbers. So you have to average, you'd have to do n times y bar, you add those up, and then you divide by the sum of your n's, the total number of points that you have. Okay, so do n times, add up n times y bar, and then divide by the total of the n's. So in our case, our grand mean y double bar is equal to 3 times 11 plus 5 times 15 plus 4 times 12, and then we would divide by 3 plus 5 plus 4. So I would get 156 over 12, and that's how I get 13. Okay, so I'm going to draw the grand mean with a blue line here. Okay, and so this is this represents the mean of all of our values. Okay, let me let's copy that. Okay, so effectively, we are going to look at the total variance. Okay, in the total variance, we're going to have this notion of sum of squares total. So if we think about our definition of variance, okay, so the definition of variance you can think of this as the average square distance from the mean, or the standard deviation before we take the square root. Okay. So we're going to have each value y minus y bar squared, and we're going to add these up, okay? And then we multiply this by 1 over n minus 1. Okay? Basically, all I'm going to do is I'm going to just take this part before the dividing by n minus 1, and this we're going to call our total sum of squares. Okay, or SST. This is the square distance from the mean for every single point totaled up. And so, you know, we could do this for all 12 data points and find the total squared distance from the mean. Okay. I'm going to try to break apart our total sum of squares, okay, into two sources of variation. Okay. One is going to be between the groups, the fact that we have 3 different diets, and one will be one source of variation will be within the groups. Just the fact that individual lambs are different from each other. Okay, and then we're going to have the total variation. Between groups variation, within groups variation, and the total variation. Okay. And so here we're going to have sum of squares. Okay. And so for our total variation, the sum of squares total, you can think of this as, this is our definition of variance in the context of, what am I saying? Oh, in the context of what we're doing here, we're going to take each individual data point y, we're going to subtract off the grand mean, and we're going to just square that difference, okay? And because of our notation, I'm going to have this sum is do all for all points in a group, and then do it, we have a second sum, and that says do it for all groups. Okay, so when you read formulas, you know, you always start on the inside and you kind of work your way out. So this basically just says take each value, subtract off the grand mean, and as you're working out, it says then square that value. So we have the squared distance from the mean, do it for all points in a group, and do it for all the groups. And this is going to be our total sum of squares. Okay. So when we look at a point, we're going to say, okay, let's look at this guy right here. This point right here, okay? This guy has a value of 9. The grand mean has a value of 13, okay? So this guy is 4 units away from the grand mean, okay? So this guy has his total distance from the grand mean is 4. From here to here is 4, okay? But what we're gonna do is we're gonna say, okay, wait. Part of that is because his group mean is 2 units away from the grand mean. And then on top of that, he himself, this lamb, is 2 units away from his group mean. Okay? So this total distance from the mean can be broken out into 2 parts. The fact that his group has an average that's less than the grand mean, and that he himself individually is lower than the group's mean right there. Okay? And so that's essentially what we're doing. We're going to split up the sum of squares, this total distance from the mean, into 2 parts. Okay? And so I think it's easiest to do the within group first. And so within group, the sum of squares for within a group is all we're going to do is we're going to take each value y and subtract off the group mean, which is y bar. So over here we have the grand mean y double bar, and over here it's just y minus y bar. Okay, so this is the fact that this guy is 2 units below his group mean, and we're going to square that difference. Okay? And then we're going to do it for every single point. Okay? Every single point within a group, and then do it for all the groups. Okay, so this is going to be SS within is equal to y minus y bar squared. Do it for all points in a group and do it for all the groups. Is that okay conceptually? Yes? All right, and then between the groups, all right, SS between, basically we're going to say, all right, this value of 11 is 2 units lower than the grand mean of 13, okay? And so what we're going to do is we're going to take the group mean y bar and subtract off the grand mean y double bar, okay? And we're going to say the group mean is 2 units lower than the grand mean. And we're going to take that difference and square it, okay? But we want to do it, so this group guy has a group mean that's 2 units lower than the grand mean. What about this guy? How is his group mean compared to the grand mean?
Which one are you pointing to?
This one right here. Okay, it's the same, right? He's in the same group. Okay, so the fact that, so when we look at each of these dots and we look at how does the group mean compared to the grand mean, because they're all in the same group, they're all going to have the same value for y bar minus y double bar. Yes? Okay, so because this part depends on their group identity, right? So so it's going to be the same for all 3 points in this group. So all we're going to do is just multiply that by n, the number of points within a group. Okay? So we're going to multiply it by the number of points within a group, and then we add it for all groups. I know it looks crazy, but it's not so terrible, okay? Huh? It looks crazy. I'm hoping my explanation kind of makes sense as far as how these formulas are coming about, okay? And then so what we can do is just for this first group, we can show that, or we can do it for all of them, but I think if I can show it that it works for the first group, then you can safely conclude that it will work for all of the groups, and therefore this relationship will hold, okay? So I'm going to copy everything here. Okay, so let's explore this and just see, is this true for, we'll take a look at our first group here. Okay, so with our data for group 1. Okay, so let's look at the total variation for group 1. The total variation that this sum of squares that group 1 contributes to the total variation is, we look at each data point, 8, 16, and 9, okay? And we look at the grand mean of 13, okay? So we would do 8 minus 13 squared plus 16 minus 13 squared plus 9 minus 13 squared, okay? And so we see, okay, 8 minus 13 is 5, 5 squared is 25, 16 minus 13 is 3, 3 squared is 9, and 9 minus 13 is 4, 4 squared is 16. So the sum of squares total for group 1 is 25 plus 9 plus 16. We get total sum of squares of 50. So this is what group 1 contributes to the total variation. Okay, let's look at the sum of squares between. Okay, so between, we would say, okay, the group mean is 13. I'm sorry, the group mean is 11 and the grand mean is 13. So we're going to do 11 minus 13, okay, squared. And how many data points we have? We have 3. Okay? So this becomes 3 times 11 minus 13 is 2. 2 squared is 4. So we have the sum of squares between the groups for group 1 is 12. And then within the group, okay, we're going to look at our 3 data points. The group mean is 11, okay? And so we're going to say 8 minus 11 squared plus 16 minus 11 squared plus 9 minus 11 squared. So this is basically the individual differences from their own group's average. Okay, so here 8 minus 11 is 3. 3 squared is 9. 16 minus 11 is 5. Squared is 25. And 9 minus 11 squared, 9 minus 11 is 2. Squared is 4. Okay, and so 9 plus 25 plus 4, we get 38. Okay, and indeed, 12 plus 38 is equal to 50. Okay. So our sum of squares between plus our sum of squares within adds up to the sum of squares total. Are you guys still with me? Okay, and so we can do this. We can do this for all of the data points and calculate the total sum of squares between the groups, and do it for all groups and calculate the total sum of squares within the groups. And then we can also, we could even do it for sum of squares total. Okay, but if we know, I'm not going to mathematically prove this to you, but I'm hoping just this kind of illustration satisfies your question, do these things equal? So, if we calculate our SS between and our SS within correctly, we can get, we can just add those two together and know that's our sum of squares total. Okay. So let's, I want to, let me take this. Our sum of squares within, this is often going to be rewritten, okay? Because our calculation of sum of squares within depends on us having the individual data points y, okay? And so to avoid this, because a lot of times we'd rather just deal with summary data. I mean, when you give it to a computer, you need the individual data points, okay? But if we're going to do things by hand, we'd rather just deal with the summary data, okay? And so we're going to go back to our kind of our relationship, or definition of standard deviation and variance, okay? So we can think of the variation as s squared. S squared is our variance. So variance is equal to s squared, which is equal to 1 over n minus 1 times the sum of y minus y bar squared. Right? So this is kind of our definition of variance, which is our standard deviation squared. Okay. So in order to get rid of this part, okay, so we don't have to deal with y minus y bar squared, I'm going to exploit the fact that this exact quantity, y minus y bar squared summed up, appears right here. Okay, so I'm going to exploit this fact, and I'm going to just say, oh, look at this. If I multiply n minus 1 times s squared, I get exactly that. Okay, and so my sum of squares within will often be written this way. N minus 1 s squared. Okay. Let me just check the textbook. The textbook might have written s squared times n minus 1, but let me just double check here. Okay, yeah, n minus 1 s squared, ss within. Okay, and so so this is often how it's going to be written. Okay, and so a lot of times we're going to be creating an ANOVA table. Okay, so our ANOVA table will have the source, which will basically be called between groups, and then we have within groups, between group, within groups, variation. This is generally referred to as residual variation. And then we will have the total, okay? Then we're going to have degrees of freedom. I'm just going to write df, degrees of freedom. Then we're going to have the sum of squares. And so I guess I'll write captions for these. Degrees of freedom, sum of squares, and this will be mean squares, and this will be called our, this is the F ratio. Okay, so we have already defined our sum of squares, and we said this is n times y bar minus y double bar squared, and this is n minus 1 s squared, and this will just be ss between plus ss total within. Okay, the degrees of total degrees of freedom will be the total number of points minus 1. Okay, so this might be written as n dot minus 1, n dot meaning total number of points. The degrees of freedom for between the groups is number of groups minus 1. Or number of groups is sometimes written as I, and it'll be I minus 1. Okay, and then the within groups degrees of freedom is always going to be is basically defined by the relationship. This plus this has to add up to the total degrees of freedom. So basically, it's, you know, however many degrees of freedom you need so that everything adds up to the total. Okay, so in this case, it's going to be n dot minus I. Okay, so basically, this plus this is going to equal this. Because, you know, between df plus within df must equal total df. So that relationship holds.
So why did you put minus?
Why did I put minus?
Yeah, for within groups if it's plus.
Yeah, because if I do this plus this, then it will add up to this.
Oh, okay.
Yeah,
Okay.
yeah. Okay, and so our our mean squares value is always going to be sum of squares divided by degrees of freedom. So you do sum of squares between divided by degrees of freedom between, and this is also sum of squares divided by degrees of freedom. Okay. So you can kind of think of this mean squares even, and if I did this to sum of squares total divided by degrees of freedom, what value would I get here? So if I, so I said this is sum of squares divided by degrees of freedom, right? And so if I did sum of squares divided by degrees of freedom for the row for the total, I would have the variance. Exactly, exactly. So if I did SS over DF, this is effectively sum of squares, total sum of squares total divided by n minus 1. This is just the variance of the entire data set. Okay, but often, when you create ANOVA tables in the computer, they often leave this total row out. Okay, just because it's kind of like this is the variance of the entire data set. This is something that you can figure out on your own or something like that. Okay, but so this is often left out. Okay, and the F ratio is always going to be the mean squares for this row. So in this case, mean squares between divided by mean squares within, or I'm going to just call mean squares residuals because this is kind of the more common term. Okay, so you're just going to take this value and divide by this value. All right, and then and it never exists for the residual row because it's always going to be a 1, right? Okay, so this is our ANOVA table. Now what do we do? Okay, so at this point, I'm just going to say that other people have figured out the sampling distribution of our F ratio, okay? And it follows what's called the F distribution. That's why it's called the F ratio. So this value will follow what's known as an F distribution, okay? And we can then, once we have this, we can go to a table, a reference table, to go from this statistic to a p-value, okay? But to be honest, you can use a computer to do it, okay? I will show you how to use the F table in a moment here. But for now, we'll take a 10-minute break here, and then we'll come back and we'll finish off this one-way ANOVA stuff, and we'll continue on there.